Today we begin Chapter 5, Light, the Cosmic Messenger. Light is the primary tool astronomers use to understand the universe. Everything we know about stars, galaxies, planets, and the cosmos comes from analyzing the light they emit, absorb, or reflect. First, what is light? Light behaves like both a wave and a particle. As a wave, it has wavelength and frequency. The distance between wave peaks is the wavelength, and the number of oscillations each second is the frequency. All light travels at the same speed in a vacuum, 3 times 10 to the 8th meters per second. The rule is wavelength times frequency equals the speed of light. As a particle, light comes in tiny packets called photons. Each photon has energy equal to h times frequency. Higher frequency means higher energy and shorter wavelength. Visible light is only a small slice of the electromagnetic spectrum. From lowest energy to highest energy we have radio, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. What is matter? Matter is made of atoms. An atom has a nucleus with protons and neutrons and electrons orbiting around it. The nucleus holds 99.9% of the mass. Atomic number is the number of protons. Mass number is protons plus neutrons. Isotopes have the same protons but different neutrons. When atoms bond together, we call them molecules. When light meets matter, 4 things can happen. Emission, matter gives off light. Absorption, matter takes in light. Transmission, light passes through. Reflection or scattering, light bounces off. A rose looks red because it reflects red light. Blue glass looks blue because it transmits blue light. Now, spectroscopy. There are 3 main spectra. A continuous spectrum is a full rainbow made by hot, dense objects. An emission line spectrum is black with bright lines made by hot, thin gas. An absorption spectrum is a rainbow with dark lines produced when cooler gas absorbs specific wavelengths. Each element has unique energy levels. When electrons jump down, they emit photons. When electrons jump up, they absorb photons. These lines form a spectral fingerprint that tells us the composition of stars. Thermal radiation. All dense objects emit light. Hotter objects emit more total light and peak at shorter wavelengths. That is Wien's law. Hotter means bluer, cooler means redder. The Doppler effect tells us motion. If a source moves toward us, the wavelength is compressed, giving a blue shift. If it moves away, the wavelength is stretched, giving a red shift. By measuring the shift in spectral lines, we find an object's radial velocity. Telescopes collect more light, improve resolution, and detect wavelengths our eyes cannot see. Refractors use lenses. Reflectors use mirrors and are the most common for large research telescopes. Radio telescopes are large dishes. Interferometry combines many telescopes to act like one giant telescope. X-ray telescopes use grazing incidence mirrors. Why put telescopes in space? Not to be closer to stars. We go above Earth's atmosphere to avoid light pollution, turbulence, and absorption of ultraviolet, X-ray, and infrared light. Space telescopes like Hubble, Chandra, and James Webb avoid these problems. Ground-based telescopes can also use adaptive optics, rapidly adjusting mirrors to sharpen images. Light is the universe's messenger. By studying light, we learn composition, temperature, motion, and physical conditions. Telescopes, especially in space, allow us to collect and analyze this light with extraordinary precision.